Okay, hello and welcome to a video I've been looking forward to make ever since we started this calculus series. Today we are going to be learning about partial fractions, my absolute favorite integration technique. I'm so excited to be doing this video for you, and without further ado, let's just jump into it. The name of this section is partial fractions, which is such a strange sounding name. So what does that actually mean? So partial fractions is a super cool, in my opinion, technique that helps us compute the integral of functions with polynomial denominators. So if you see a polynomial function in your denominator and that's the only thing there, then you might consider using partial fractions. However, some of these integrals can be solved using u substitution. For example, if you have the integral of x over x squared plus 4, the denominator is a polynomial, but you can solve this using u substitution. U equals x squared plus 4, du equals 2x dx. This is going to be equal to 1/2 ln, absolute value of x squared plus 4. So we can do this just using u substitution. However, as we know, u substitution is not universal, so we can use partial fractions instead. So the idea of partial fractions is if we have a very large fraction in our integrand, which has a polynomial denominator and a polynomial numerator, we can decompose that into the sum or difference of smaller fractions, such that taking the integral of those smaller fractions is easier than taking the integral of that huge fraction. So we're decomposing the fraction down, and to do that we'll have to use quite a bit of strategy and algebra, which are two things I really like, so that's why I love partial fractions. And as I said, partial fractions requires the most algebra out of the integration techniques that we'll learn. So let's take a look at a fraction decomposition chart. When we have an integrand with a polynomial denominator, our first step will be to try to factor it as much as possible. And then we'll look at each factor in the denominator. And each factor in the denominator will produce at least one term that will sum together, right? So the idea is we take something like the integral of x divided by this quantity, and we see there are three factors in the denominator. So each one of those factors will produce one smaller fraction. So it'll create one smaller fraction which will sum together. So here we have three distinct factors in the denominator, so we expect to have at least three fractions that will sum up. But how do we get these fractions? Well, we take a look at the fraction in the denominator. If the term in the denominator is of the form ax plus b, then we're going to say that that produces the fraction capital A over ax plus b, where capital A is the constant that we're going to solve for. So these are corresponding terms when we're decomposing our fraction. When we see an example, this will start to make sense, I hope. If we see a factor in the denominator that's like this, ax plus b to the power of k, well, that's going to produce k fractions that will sum together. The first fraction will be a1 over ax plus b, and then we'll add to that a2 over ax plus b squared, and so on until ak over ax plus b to the power of k. So this is, I guess, one term in our denominator. Technically it's k, but that will produce k terms in our sum. If we see ax squared plus bx plus c, that creates this term, ax plus b over ax squared plus bx plus c. And if we see that same thing to the power of k, it's just like the first two examples where we have this term which repeats k times, it's just the denominator's power that's changing. So this is how we decompose our fractions based off of the terms. So let's take a look at some examples of some fraction decomposition. Let's say this was our integrand. We know, and we want to factor our denominator to look at its factors. So we know that x squared minus 2x minus 8 is equal to x minus 4 times x plus 2. So we're essentially taking the integral of 1 over x minus 4 times x plus 2 dx. Now we want to decompose this fraction, so we'll take a look at the first factor in the denominator, which is x minus 4. Looking at our decomposition chart, that's of this form. So our corresponding fraction will be capital A over ax plus b, or capital A over x minus 4. Similarly, our x plus 2 term is also of this first type, so we give it a different fraction. This time we'll give it b over x plus 2. Note that we're giving it the letter b. We don't want to give it a, because that would indicate that the numerators of these two fractions are identical when they may not be. These are just temporary variables that we're giving the numerators. We eventually have to solve for them. And for that we'll do some algebra, and we'll get to that soon, but that's how we're just denoting these numerators, with these capital variables. So that's the first example. Okay, let's take a look at the one right below it. The denominator factors into, well, we can factor in x squared out of the first two terms to get x minus 1, and then we can factor out a 2 from the second two terms to get x minus 1. So this all comes together to x squared plus 2 times x minus 1. So we're taking the integral of 1 over x squared plus 2 times x minus 1 dx. You can assume that there's like an integral in front of all of these. I'm just showing how we're decomposing the fraction. It's just, like right now this is just algebra. We're just taking a fraction and making it the sum of many. So now we take a look at the factors in the denominator. First one is x squared plus 2. If we look at our decomposition chart, that's of this third form because the power of x is 2. That's the greatest power in our factor. So for that, we need to give it two terms in the numerator, ax plus b, and then the denominator stays the same. So that's where we get here, this bx plus c over x squared plus 2. X minus 1 is of that first form, so that's going to be a over x minus 1. In this third example, our denominator is already factored for us, kind of, so we can take a look at the decomposition chart, and it's of this form, right? Ax squared corresponds to this x squared, bx corresponds to 2x, c corresponds to 3, and k is 2. So that means we're going to have two fractions to sum up, and the first one's going to be ax plus b over our denominator to the first power, and then we'll add another term. Here the decomposition chart gives a2, b2. I just like to use different letters, so I'll use c and d, so that's why we see down here cx plus d over x squared plus 2x plus 3 squared. And then same thing goes with our last example here. This is kind of already factored. If we scroll up, it's the second case in our decomposition chart. The power was 3, so it's going to be 3 terms for summing together. It'll be 1, 2, 3. Notice the power of the denominator is changing upwards, and we see that here. 1, 2, 3. Our numerators are a, b, and c. So this is technically the first step of our partial fractions solving with integrals. We're going to claim that we can decompose our integrand into the sum of two fractions. We'll solve for a and b, and then we'll just say, okay, the integral of that left-hand side is equal to the sum of the integrals of the right-hand side. And you can see, let's just pretend that a was equal to 1 and b was equal to 1. Then taking the integral of the left-hand side is a lot more challenging than taking the integral of the right-hand side, because the right-hand side we can just see by inspection this is ln of x minus 4 plus ln of x plus 2. And if a and b were different, those would just be things that come out in front of the integral multiplied together, so it's a really easy integral to compute. I'm not actually sure what the actual values of a and b are in this example. I would have to compute them out. But that's just to demonstrate how easy it becomes to compute these integrals. Let's see an example and then try some for our own. So this is the integral we want to evaluate. 1 over x squared minus 5x plus 6. We see a polynomial denominator. We can tell that we can't use substitution because there won't be anything to cancel. So we can try to factor our denominator, which works really nicely. It comes into x minus 3 times x minus 2. We'll now claim that this following equivalence is true for some a and b. that 1 over x squared minus 5x plus 6 equals a over x minus 3 plus b over x minus 2, where these fractions are coming from our fraction decomposition chart. X minus 3 and x minus 2 being the two of the factors, both fall under this first row, so that's the fraction we give them. So then the integral of the left-hand side is simply equal to the integral of the right-hand side, which we can split into two easier integrals. But now we have to solve for a and b, so how are we going to do that? Well, let's consider the sum of the two fractions and combine it back into one fraction. So we started with one fraction, decomposed it into two, now we're putting that back into one fraction. Yeah, we need to, because we need to solve for a and b. So if we multiply this first term by x minus 2 over x minus 2, and this second term by x minus 3 over x minus 3, we get this fraction here, which expands into this. But remember that this sum we claimed was equivalent to our integrand. So that means the integrand should be equivalent to our fraction we obtained here. And notice the similar denominators, which is a good sign. Now we just have to make the numerators match. So this numerator should equal 1, right? So that's what we claim right here. With this information, we can solve for a and b because we can create some equations, right? So this is where we were here, and we can, factor out an x from these two terms and whatnot. So we get x times a plus b minus 2a minus 3b equals 1. We can solve for a and b because we have these systems of equations. A plus b equals 0 and negative 2a minus 3b equals 1. How did I get these equations? Well, looking here, we see this first term is x times a plus b. But there's no x term on the right-hand side, and there's no other x terms on our left-hand side. So whatever we multiply by x, well, it should be 0 because we don't want any x's on the left-hand side because there's none on the right-hand side. Hence, a plus b should equal 0. We have minus 2a minus 3b. We know that a and b are going to be constants, so this product and sum will be a constant, and we're targeting for that to equal 1. Hence, that's how we get the second equation. We can solve these systems of equations using just normal algebra techniques. Get a equals 1, b equals negative 1. Then we return to our integral. So this is what we started with. We claimed that that was equal to the sum of two integrals up here. Now we're substituting in what we solved for a and b, a being 1, b being negative 1, and finally we take the integral of the right-hand side, and we get this super nice answer, which we can combine into one term, but that doesn't really matter. That's the idea of partial fractions. As you can see, there's a ton of preparation that goes into it, and then the final step is just taking this simple integral. So it's the first steps that you really need to master. And as you can see, there can be a lot of algebra. Getting this numerator, solving these systems of equations. So it is easy to make mistakes, which is why it's always important to just take your time and maybe check your work. That's partial fractions. We're going to do a handful of examples. Fair warning, some of these examples are long, but that's just how partial fractions work, and that's why I love it so much. So here we go. Evaluate the following integral, 5x minus 1 over x cubed minus 9x. First thing you should be thinking is, can I do u substitution? Well, not really. What would you let u equal? I mean, you'd want to let u equal the denominator, but when you take the derivative of that, it's not going to cancel with the numerator, so you might have to do a substitution with x in terms of u. That just seems messy. And you can go down the pecking list. Integration by parts, sure, but who wants to do integration by parts? And then some of the other techniques might not work. So we see a polynomial denominator, so we're starting to think partial fractions. So the first thing we should do is try to decompose our fraction. So for that, we should try to factorize our denominator. So our denominator is x cubed minus 9x. The first thing I see is I can factor out an x to get x times x squared minus 9. And I see x squared minus 9 is the difference of two squares, so we know that factors out into x plus 3 times x minus 3. So really, we're taking the integral of 5x minus 1 over x times x plus 3 times x minus 3. And we're going to claim that we can decompose this fraction into the sum of some fractions. In this case, at least 3, because there are 3 distinct terms in our denominator. So let's find these fractions. Let's look at the first term, which is x. Scroll back up to our fraction decomposition chart, and we see that falls under the first row. So the denominator is our term, so the denominator will just be x, and the numerator will just be a. While we're here, let's think about the other two terms, which are x plus 3 and x minus 3. Both of those also fall under this first row, so they will get similar fractions, the denominator being that term, and the numerator being some other constant, say b or c. So with all of that in mind, we're going to say that this fraction is going to be equal to a over x plus a b over x plus 3 plus c over x minus 3. That's our idea. But now we have to solve for a, b, and c. So how are we going to do that? Well, as we saw in the previous example, we should combine it into one fraction and then solve the numerator. So how should we do this? First, we need to find the common denominator. So if these are our 3 functions, the common denominator will actually be this, x times x plus 3 times x minus 3. You'll see this happen a lot, where the common denominator is what we started with, which makes sense because we just decomposed the fraction and we're trying to compose it again. So we need to multiply the numerator and the denominator of this first term by x plus 3 times x minus 3, right? So this will become a times x plus 3 times x minus 3 over x times x plus 3 x minus 3. The second term, we want to multiply this by x times x minus 3 over x times x minus 3. So this will be b times x minus 3 over x plus 3 times x minus 3. And the last term we want to multiply by x times x plus 3. X plus 3, and on the denominator we have x minus 3 times x plus 3. So now you can see that we can combine these fractions together into one because the denominators are the same all across, right? This combines into one fraction. So why don't we do that? This becomes a times x plus 3 times x minus 3 plus b times x minus 3 plus c times x plus 3, all of this over x times x minus 3 times x plus 3. Now let's expand out our numerator. So we get a times x plus 3 times x minus 3 is x squared minus 9. So why don't we just take care of this all together? This will become ax squared minus 9x. Ax squared minus 9x. B times x minus 3 will be bx squared minus 3bx. And then cx times x plus 3 will be plus cx squared plus 3cx. All of this over, and you can compute out the denominator if you want, but you'll see that it is equal to x cubed minus 9x, which is what we're targeting. Good. So our numerator must be equal to 5x minus 1 because we claimed that this fraction decomposes into this. So we need the sum to be the same thing. So this implies, or what we want is ax squared minus 9x plus bx squared minus 3bx plus cx squared plus 3cx. We want that to equal 5x minus 1. And as we saw in the example, this should induce some systems of equations. So let's try to obtain those systems of equations. And the way I like to do it is to factor out x terms and then combine them together. So the highest power x term is x squared. So I'm going to factor out an x squared from the terms that have it, those being ax squared, bx squared, and cx squared. Sorry, not that 3cx. So this becomes x squared times a plus b plus c. Then I'll factor out an x term from those that have it. So this minus 9x, this minus 3bx. Oh wait, sorry. This 9 should be a 9a. This is a 9a here. There we go. So the terms that have the x are minus 3bx and this 3cx. So this would be minus 3b plus 3c. And then finally we have the constant terms, which is just that minus 9a. And that should equal 5x minus 1. Now it's easy to form the system of equations because we see here we have this x squared times some constant, but that constant must be 0 since there's no x squared term on the right-hand side. Similarly, we see an x times some constant, so that constant must be a 5 since that's what we see on the right-hand side, and this minus 9a should equal minus 1. So we can write that out. I'm going to add a page because we are going to need more room. So this tells us that a plus b plus c is equal to 0, minus 3b plus 3c equals 5, and minus 9a equals negative 1. Well, using that last equation, we can solve for a and tell that a equals 1/9. Which means if we look back at the first equation, b plus c equals a negative a, but since a equals 1/9, we can say b plus c equals 1/9. And the second equation has 3's in front of the b's and the c's, so this left-hand side looks similar to this, the other left-hand side of the first equation. So let's convert that first equation into 3b plus 3c, and that's going to equal negative 1/3. Okay, so let's write this down below. 3b plus 3c equals negative 1/3. Looking at the second equation, we have negative 3b plus 3c equals 5. So if we sum these two equations together, the 3b's cancel and we're left with 6c equals, we're summing them, so this would be 14 over 3, which tells us c equals 14 over 18, or 7/9. And lastly, we just have to solve for b. We can use the first equation where a plus b plus c equals 0. A is equal to 1/9, and c is equal to 7/9. So that means b equals negative 8/9. So we have our a, b, and c computed, which is great, because now we can turn back to what we started out with claiming, and we have fully decomposed this fraction because now we know what a, b, and c are. So I'm going to take all of this and duplicate it and bring it down here. Right? So this fraction now becomes equal to, a is 1/9, I believe, so we can write this as 1/9 times 1 over x. B is negative 8/9, so this is negative 8/9 times 1 over x plus 3. And then c is 7/9, so this is plus 7/9 times 1 over x minus 3. Which means this integral, 5x minus 1 over x times x plus 3 times x minus 3 dx is equal to the integral of 1 over 9x, I'm just combining these together, minus 8 over 9 times x plus 3 plus 7 over 9 times x minus 3. So this will be equal to the integral of 1/9 times 1 over x, so we can just bring the 1/9 out in front, dx, minus 8/9 integral 1 over x plus 3 plus 7/9 integral 1 over x minus 3 dx. And these integrals are a lot easier to solve. You can substitute them if you want, where u will just be your denominators, or you can realize that they all have x to the power of 1 in the denominator, which indicates the answer will be some form of ln. And if you recognize like how the chain rule works, you can just see that it'll be ln of that denominator quantity. But these integrals are much easier to solve. I'll let you solve them on your own. But this answer will be equal to 1/9 ln of absolute value of x minus 8/9 ln absolute value x plus 3 plus 7/9 ln absolute value of x minus 3. Don't forget your plus c because it's an indefinite integral. And boom, we are done. That's our first partial fractions example. You can see it requires a lot of work and a lot of effort, but it's really cool how it works, because we're just decomposing the fraction down into a bunch of easy fractions to take the integral of, and it's just a bunch of algebra. So if you're good at algebra, you'll be good at this. If not, that's okay, it'll just take some practice. But begin to notice some of the patterns of how this works. Factorizing the denominator, creating your sum of fractions by looking at the table, and then combining those fractions again into one massive fraction, looking at the numerator, create your systems of equations, solve for the variables, and integrate. That's going to be the general game plan. So let's do a couple more examples, because I understand this can be a tricky concept, and there's a lot to get to. So here we go. We should tell pretty easily that u substitution just won't work, and I don't even want to think about integration by parts. So this is what we have to deal with. Let's think about partial fractions. We see a polynomial in the denominator, we see one in the numerator. Partial fractions should work out pretty easily. Well, easily might be debatable, but we should be able to do it. So the first thing we did in the previous example with partial fractions is we factorized the denominator. So let's do that. X cubed plus 2x squared plus x. Well, I can factor out an x from all of these terms to get x times x squared plus 2x plus 1. And I notice that that second term is equal to x plus 1 quantity squared. Okay, so our fraction becomes 5x squared plus 20x plus 6, and then the denominator can be rewritten as x times x plus 1 squared. And we're going to claim that this equals the sum of some fractions, but for that we need our decomposition table, and for that we have to look at each factor of the denominator. So the first one is just x. If we scroll back up to our chart, we see that's in the first row, ax plus b, so that'll give us this fraction. So our fraction should be capital A over x, because that's the factor in the denominator. So the first term will be a over x. And the second term, well, the second factor is x plus 1 quantity squared. So if we scroll back up, that falls under this second row, where x plus 1, so a is 1, b is 1, k is 2, because it was x plus 1 squared. So that will produce two terms in our fraction, right? Because this goes up, this sums up till k, but k is 2 here. So we need a constant over ax plus b, which in our case is x plus 1. And then we need another constant over ax plus b squared, which would be x plus 1 squared. So if we scroll back down here, let's give the constant b instead of a with a subscript. And the first one was just x plus 1 in the denominator. And the second one was x plus 1 squared in the denominator. So that's how we're decomposing our fraction. We're going to claim that these are equivalent for some a, b, and c. Now our job is to solve for that a, b, and c. So to do that, we need to combine it into one fraction. And for that, we need like denominators. So what is the common like denominator? Well, we can take a look over here and see that x times x plus 1 squared would be a valid denominator. So for this first fraction, we can multiply it by x plus 1 squared over x plus 1 squared. X plus 1 squared over x times x plus 1 squared. And then we'll add to that b times something, Well, so the denominator of that b fraction is x plus 1, and this is the fraction we're targeting. So we should multiply it by x times x plus 1 over x times x plus 1. We don't need the squared because there's already an x plus 1 term there. So this would be b times x plus 1 over x plus 1 times x plus 1. And we can see that these two terms are alike, so we can just combine that into x plus 1 squared. Whoa. And now we see that these first two fractions have like denominators. For this last fraction, the denominator is just missing this x piece, so we'll multiply the numerator and denominator by x. So this will be c times x divided by x plus 1 squared times x. And now all fractions have common denominators. We can combine this into one massive fraction, a times x plus 1 squared plus bx times x plus 1 plus cx, all of this over x times x plus 1 squared, which we said was equivalent to the denominator of our original fraction. And we can expand this fraction a little bit more, especially in the numerator. X plus 1 squared is x squared plus 2x plus 1. So let's just multiply that through by a. So we'll get ax squared plus 2ax plus a. Bx times x plus 1 is bx squared plus bx. And then we add on that cx, and the denominator stays the same. Remember, we're targeting our numerator to be equivalent to the numerator of the integrand, because that was the fraction that we were decomposing. So that we claim that the numerator of ax squared plus 2ax plus a plus bx squared plus bx plus cx should be equal to 5x squared plus 20x plus 6. And now on the left-hand side, we can do that factoring trick where we take out the x terms. So first we'll take out an x squared term from those that have it. So that would be x squared times a plus b for these two terms right here. Then we'll take out an x term from those that have it. So it'll be x times 2a plus b plus c for these three terms. And then we only have one constant term, which is just the plus a, and we say that that should equal 5x squared plus 20x plus 6. And now this induces a system of equations, right? This x squared times a plus b, on the right-hand side, the coefficient of the x squared is a 5, so we need a plus b to be equal to 5. A plus b should be equal to 5. For our second term, we see a 20x on the right-hand side, so that means this 2a plus b plus c should also be equal to 20. 2a plus b plus c equals 20. Lastly, we see a 6 on the right-hand side and only one constant term on the left-hand side, which tells us that a should equal 6. So great, we already know what a is, we just need b and c. Looking at the first equation, if we substitute a equals 6, we get 6 plus b equals 5, or b equals negative 1. So we have b, we have a, we can solve for c using the second equation by saying 2 times a, which is 6, plus negative 1 plus c equals 20, which tells us that c should equal 9. So we have a, we have b, we have c, we have our fraction decomposition. We're ready to substitute and integrate. So let's go back up here, duplicate. Alright, so that's what we started by claiming, which would imply that the integral of the left-hand side is equal to the integral of the right-hand side. Now we have a, b, and c, so we know what the decomposition actually is. So let's substitute a, b, and c back in, integrate, and solve. Okay, so we had a is equal to 6, so this is 6 over x. B is equal to negative 1, so we can make this minus 1 over x plus 1. And c is equal to 9, so this is plus 9 over x plus 1 squared. Okay, you know how much I like to break apart an integral into the sum or difference of many, so that's what we'll do here. We can also bring out some of these multiplicative factors. So this becomes 6 times the integral of 1 over x dx minus the integral 1 over x plus 1 dx plus 9 times the integral of, well, yeah, let's write it as x plus 1 to the negative 2 power dx. So this first integral is simply just 6 times ln absolute value of x. The second one is pretty similar as well. That'll just be ln of x plus 1. This last one will require a little bit more effort, but it's honestly not too bad. We can do a little bit of u substitution with u equal x plus 1 and du equal dx. So this would be 9 times the integral of u to the negative 2 power du. Okay, and now that's just a simple power rule. We add 1 to the numerator, which becomes negative 1, and then we divide by that power, so we divide everything by negative 1. So we can just make that a minus 9 instead of a plus 9. And then we have u to the negative 1 power, but we can substitute what we had in for u, which was x plus 1 to the negative 1, or we can just write that as a fraction, which is times 1 over x plus 1. Here we have 6 ln absolute value of x minus ln absolute value of x, and then we can just rewrite this a little bit. X plus 1 minus 9 over x plus 1. Don't forget your plus c, and that is your answer. Again, the actual integration we did was very easy. These integrals we either solved immediately or did a simple u substitution. It's just all of the preparation that goes into it. So again, just be careful with your algebra, but as you can see, the pattern is pretty similar. Let's do a couple more examples just to solidify this concept, and then we'll call it a day. Here we go. This one looks a little bit more daunting than the previous one, so it's slowly ramping up. But again, you can start to think about your other integration techniques, and they won't work as nicely as partial fractions will. So yeah, the first thing that we normally do is factorize our denominator, which it already looks like it's factorized, but we can factor it a little bit more, because we can say that x squared minus x times x squared plus 4, well, we can factor out an x from the first term, and we have x times x minus 1 times x squared plus 4. It's really important to factorize it as much as possible, because when we look at the why do I keep on saying fractal? When we look at the fraction decomposition chart, it matches better with the fully factorized version of our denominator. Wow, lots of F words. Like fraction and fractal, that's what I mean. Anyways, we're claiming that 2x cubed minus 4x minus 8, I think that's staying in, over x squared minus x times x squared plus 4 is going to be equal to the sum of some fractions. Rather, let me change this x squared minus x in the denominator to x times x minus 1. And for these smaller fractions, we need to look at our chart, and that's based off of the factors. So the first factor is x, and x minus 1, we'll look at that as well, because if we look back at the chart, we'll see that they fall under the same exact row, being the first row. So each one will get a distinct numerator, but the denominator will be that term. So the x term will become a over x, and the second term will become b over x minus 1. And now the curious term is this last term here, x squared plus 4, which we can take a look at our chart. And we see it's of this form here, where the highest power of the x is 2, so it's this right here. And we note that the numerator now needs ax plus b instead of just an a, and the denominator is just simply that term. So if we scroll back down here, this we can say is cx plus d over x squared plus 4. Let me just stop here for a moment to point out something. You'll notice that the decomposition chart only went up to where the highest power of x was 2. Let's say that our denominator factored into x times x minus 1 times x cubed plus 2x plus 4, or something like that, right? So the first two terms would stay the same just by the chart, but the chart would not tell us what to do for this third term. So the way I like to do it is you look at the highest power of x in your factor, so in this case it's x cubed, and then you notch it down by 1, so think about x to the power of 2, and that will be the first part of your numerator. So that will tell us we need an x squared term in our numerator, but we also need everything below it. So we need an x term, and we need a constant term. So we can just add our coefficients in front of here, and then the denominator stays the same. Okay, so that's how that would go. And if this was x cubed plus 2x plus 4 squared, again, that would not be in the decomposition chart, but the same idea holds, where this to the power of 1 produces one term, and this to the power of 2 provides a second term. So this would be your first term, and your next term would have x cubed plus 2x plus 4 squared in the denominator, and the numerator would be of a similar form. So this would be fx squared plus gx plus h. So that's just a little tangent on how you would handle these fractions with higher powers than just 2. Okay, anyways, we've decomposed our fraction, we've claimed this equivalency, we have to solve for a, b, c, d now. To do that, we will combine them into one fraction. So this first term, a over x, we're going to multiply that by x minus 1 times x squared plus 4 on the numerator and the denominator to get the common denominators. On the second term, we will multiply that by x times x squared plus 4. And we can start to see that the first two terms have similar denominators now. And the last term, we're simply multiplying that by x times x minus 1, and same with the denominator. And you can see now that all three terms have the same exact denominator, so we can combine them into one. So this will be a times x minus 1 times x squared plus 4 plus bx times x squared plus 4 plus cx plus d times x minus 1, all of this over x times x minus 1 times x squared plus 4. Okay, so that's our decomposition back into a composition. Great, so we have to solve for a, b, c, and d. The way I like to do it is just expand everything out, set that equal to the numerator, and go from there. So let's expand out that numerator. So x minus 1 times x squared plus 4 is x cubed minus x squared plus 4x minus 4. And then we can distribute the a in all together. So this will become ax cubed minus ax squared plus 4ax minus 4a. Then we have bx times x squared plus 4, which is bx cubed plus 4bx. Then we have cx plus d times x plus 1, which would be multiplied by x squared minus x. And then we can distribute that in, so I'm just going to shift this upwards to reference. But this would be plus cx cubed plus dx squared minus cx squared plus dx. So that's expanding out our numerator. All of this goes over our denominator. But we don't really care too much about the denominator right now. We just care that this numerator should be equal to what? The numerator should be equal to the numerator of our integrand, which is 2x cubed minus 4x minus 8. 2x cubed minus 4x minus 8. And remember, now we can start to get our system of equations. But for that, we like to factor it out a little bit. So we look for the highest power x term on the left-hand side, which is an x cubed. So we'll factor out an x cubed from the terms that have it, being ax cubed, bx cubed, and cx cubed. So this becomes x cubed times a plus b plus c. Then we'll add to that x squared times, this term has an x squared, and these two do as well. So this will be x squared times minus a minus c plus d. Now we search for our x term, which is found in this 4ax, 4bx, and minus d. So this is x times 4a plus 4b minus d. And lastly, we look for our constant term, which is just a minus 4a, and that should be equal to 2x cubed minus 4x minus a. And as we've seen, this induces a system of equations. So we can find those by looking at the terms of the left-hand side, comparing them to that of the right-hand side. So our x cubed term on the left-hand side has coefficient a plus b plus c, which on the right-hand side tells us should be equal to 2. So we get a plus b plus c equals 2. Notice on the right-hand side there's no x squared term, which means that on the left-hand side the coefficient should be equal to 0. Therefore, minus a minus c plus d equals 0. On the left-hand side, we have this 4a plus 4b minus d term. That should be equal to minus 4. So 4a plus 4b minus d equals minus 4. And lastly, we have that minus 4a equals minus 8. So minus 4a equals minus 8. That last equation there, by dividing by negative 4 on both sides, tells us that a equals 2. So we can use that to simplify some of the previous equations. So the first equation, we can replace an a with 2, and then subtract 2 on both sides to say that b plus c equals 0. In the second equation, replace an a with a 2, so we get minus 2 minus c plus d equals 0, but if we add 2 on both sides, we get minus c plus d equals 2. In the last equation, we can replace 4a with 4 times 2, which is 8, and then subtract 8 on both sides to get 4b minus d equals negative 12. Cool. So we have one known variable, but we still have 3 unknowns and 3 equations to work with. So it should be doable. And we can look at the first 2 equations and notice that if you sum them together, the c's will cancel and we'll get b plus d equals 2. Which is nice because we can use that in tandem with this third equation, which only has b and d in it. So if we write that underneath it, equals negative 12, we can now sum together these 2 equations to see that 5b equals negative 10, or b equals negative 2. Cool. If we had b plus c equals 0, that tells us c equals a negative b, which tells us c equals 2. And lastly, if we had negative c plus d equals 2, that means negative 2 plus d equals 2, which tells us d equals 4. So we've solved for all of our constants that we were looking for. These are our constants. A lot of algebra just to get these, but now we can return back to the integral. So we scroll back up here. This is what we started out by claiming, and indeed we have found those a, b, and c's. So if we were to take the integral of both sides, which is what we're targeting, the left-hand side is what we were asked to solve, they should be equivalent. So we can do that, but now we can replace a, b, c, and d with what we have. So this is equal to the integral, and you know I like to split apart my integral, so I'm going to do that right now. Integral of 2 over x dx minus the integral of 2 over x minus 1, so that minus 2 from b just came out in front, plus the integral of 2x plus 4, substituting c and d, over x squared plus 4. Okay, so from the first and second integrals, I can bring out a 2, so I'm going to do that. This is 2 times 1 over x minus 2 times 1 over x minus 1. And in fact, we can solve the first 2 pretty easily. This is 2 times ln of absolute value of x minus 2 ln absolute value of x minus 1. But now we have this last integral to deal with, which is not as easy. So I'm going to bring this, no, I don't want to use red. I want to use, let's use this blue color. So I'm going to highlight that in blue, and we're just going to take that off to the side to solve. 2x plus 4 over x squared plus 4. How are we going to solve this? Well, let's think maybe u substitution. Well, that might work, but it won't because it's not going to cancel the numerator. So that's not good. Integration by parts doesn't seem fun. And you might be thinking, oh gosh, do we have to do partial fractions again? No. and there's a couple of reasons for that. One, we already did partial fractions, and we tried to factorize the denominator as much as possible, which goes hand in hand with the second part of why we can't use partial fractions, because we can't factorize the denominator anymore. That's already as far as it goes. X squared plus 4, you can't factorize it further. So how can we solve this? Do we just not know how to solve it? We do. And this is one trick that is so simple, but a lot of people overlook it when solving integrals. This is already the sum of some fractions. We can decompose this into the sum of fractions, but now we don't have a constraint on what the denominator should look like. With partial fractions, we put that constraint that the denominators have to be this. This is equivalent to the integral of 2x over x squared plus 4 over x squared plus 4. Such a simple thing, but for some reason, a lot of people just forget you can do this thing, because it's not extremely intuitive. If we saw this, our brains are just like wired in such a way that we automatically will combine this into one fraction. But when we see this, our first instinct for some reason is not to decompose it. So that's why you have to be extremely careful with things like this. And now we can solve these integrals individually, right? So we can put in our dx here, and like now we have a valid equivalence, and we can solve these individually. So I'm going to underline the first one in purple, so we'll solve that one in purple. So the integral of 2x over x squared plus 4 dx, you could bring out the 2 in front, but I don't want to for one reason, because we're going to solve this using u substitution, where x squared plus 4 will be our u, which means du will equal 2x dx. And if we return back to our integral, this gives us the integral of 2x divided by u times du over 2x. And now you can see why I didn't want to bring the 2 out in front, because the cancellation works a lot easier this way. I mean, it works the same if you bring the 2 out in front, it's just cleaner. So now we have the integral of 1 over u du, which is ln absolute value of u, which is ln of the absolute value of x squared plus 4. Now we have to solve the other integral, which I'll do in pink. So this is the integral of 4 over x squared plus 4 dx, and now I will actually bring out that 4. Now this one's a little bit tricky, but it almost isn't. The denominator is the sum of two squares. So let's just suppose I let u equal x and a equal 2. Then our integral is equivalent to 4 times the integral of 1 over u squared plus a squared. Well, we know what that is. That's simply going to be equal to 1 over a times arctangent of u over a. And now we can substitute in our u and our a. So this is 4 times 1 over 2 times arctangent of x over 2. So now using these two that we just solved for, we have this. So that tells us the integral of 2x plus 4 over x squared plus 4 dx is equal to ln of the absolute value of x squared plus 4 plus 4 times a half is 2, so 2 arctangent of x over 2. And we were solving this integral because it belonged to this sum up here. So we can continue by completing this sum and saying that our final answer is 2 ln of x minus 2 ln of x minus 1 plus ln of x squared plus 4 plus 2 arctangent of x over 2 plus c, and there we go. That's your answer. So a little bit trickier here, doing a lot more algebra, but the pattern stays the same. It just stays the same. And you can see, once again, still need to know your integration techniques, got to know your arctangent, things like that, use substitution. It's all building on top of each other. One last question, and I promise this one isn't as complicated as the previous one, but it's still a good one to go over, so let us do it. By now we should know that this is going to be partial fractions, and thankfully I've already given to you the denominator factorize, x squared plus 2 quantity squared. So now we just have to decompose it. So we're going to claim that 8x cubed plus 13x over x squared plus 2 squared is equal to the sum of some fractions. Without looking at the fraction decomposition chart, we're going to do this on our own, and then maybe we'll check it if we feel like it. So really, we only have one term here, but it's raised to the second power. So that means it's going to provide us two fractions. So let's write two fractions. The first fraction will be the term of the denominator raised to the first power, and then it'll be to the second power. We remember that it keeps on increasing. So the first one will be x squared plus 2, and then this will be x squared plus 2 squared. On the numerator, the way we look at it is we find the highest power term of x, which is x squared in the denominator. We subtract 1 to that power, which is x, so we should have an x term and the constant term, which is the term right below it. So we need an ax plus a b, and then same thing for the other term, cx plus d. Let's scroll back just to make sure we're correct. Yes. So this is the case that we're under, x squared plus, or sorry, this one, x squared plus 2 squared. And we can see we have this ax plus b, and there's going to be two terms since k is equal to 2, and that's what the denominator looks like, so we were correct. Cool. So we've claimed our equivalence. Now we have to solve for a, b, c, and d. For that, we can create like denominators and sum them together. In this case, the like denominator will be x squared plus 2 squared, which the second term already has, so we just need to adjust this first term. So we can multiply that by x squared plus 2 on the numerator and the denominator. So that'll look like this. X squared plus 2 times x squared plus 2. And then the second term will stay the same. And we can see now that these two fractions can combine into one. So ax plus b times x squared plus 2 plus cx plus d all over x squared plus 2 quantity squared. Let's expand out our numerator. So ax plus b times x squared plus 2 becomes ax cubed plus 2ax plus bx squared plus 2b. Then we add on that cx and that d, and the denominator stays the same. But we don't care too much about the denominator, we really care about the numerator, because we want that numerator to be equivalent to the numerator of our integrand, which in this case is 8x cubed plus 13x. Let's do some manipulation of the left-hand side. There's only one x cubed term, so that's ax cubed. There's only one x squared term, which is bx squared. There are two x terms, so we'll add to that x times 2a plus c. And then there are two constant terms, 2b plus d. And that's going to be equal to 8x cubed plus 13x. From there we get our systems of equations. So the first one is a is equal to 8 by the x cubed terms. B is equal to 0 for the x squared terms. 2a plus c is equal to 13 for the x terms. And then 2b plus d is equal to 0 for the constant terms. Looking at the last equation, b is equal to 0, so 2 times 0 plus d equals 0, which tells us that d is also equal to 0. And for the third equation, we know that a is equal to 8, so 2 times 8 plus c equals 13, which tells us c equals a negative 3. So we have a equals 8, b equals 0, c equals a negative 3, d equals 0. Now we can return to our decomposition. Duplicate that. We claim this equivalency. We're trying to compute the integral of the left-hand side, which would be equal to the integral of the right-hand side. We know what a, b, c, d are, so we can compute these integrals. So this will be equal to the integral of 8x plus 0 over x squared plus 2 dx plus the integral of negative 3x all over x squared plus 2 quantity squared dx. I'll just make this look a little bit nicer. 8 times the integral x over x squared plus 2 dx minus 3 times the integral x over x squared plus 2 quantity squared dx. We can solve these individually, so I'll do the first one in this purple color here. So the integral of x over x squared plus 2 can be solved using u substitution. We'll let u equal x squared plus 2, which tells us du equals 2x dx. So our integral now becomes the integral of x divided by u times du over 2x, which is equal to 1/2 integral 1 over u du, which is 1/2 ln of the absolute value of u, and substitute back in our u, which is x squared plus 2. For the other integral, we'll solve that using this blue color. So the integral of x over x squared plus 2 quantity squared dx. And this one we can also solve using u substitution. So u again will equal x squared plus 2. Du again will equal 2x dx. Our integral becomes the integral of x over u squared times du over 2x, which is equal to 1/2 the integral of u to the negative 2 du. And now we use the power rule, so this is negative 1/2 times 1 over u, which is equal to negative 1 over 2 times x squared plus 2. And now we can put it all together. This is what we were trying to solve for, so let's bring that down here. So this will be equal to 8 times 1/2 ln absolute value of x squared plus 2 minus 3 times, I should have used blue or black for this, minus 3 times negative 1 over 2 times x squared plus 2. And we can compute this all out. This is 4 ln absolute value of x squared plus 2. Minus 3 times minus 1 is plus 3, so this is plus 3/2 times 1 over x squared plus 2. Don't forget your plus c. And that's your answer. There we go. That is partial fractions for you. It's a lot of algebra, it's a lot of work, but it's really, really rewarding, and I think it's one of the coolest methods to solve these integrals. So remember, if you see polynomials, especially in the denominator and in the numerator, think partial fractions, and make sure you're checking your algebra because it's so easy to make mistakes on this. The best way to check your algebra is once you solve for a, b, and c, plug them into here and actually add these fractions together to make sure that you get the integrand that you're looking for. I didn't do that here because it just takes a little bit too long, and this video is already super long, but this is the best way to check your work, because if you see that the sum of these fractions don't equal your integrand, then you have the wrong values for a, b, c, and d, and you'll have to redo a little bit of work. So that's the biggest tip there. There you go, that's partial fractions. I hope you enjoyed it as much as I did. A really cool integration technique, and we're slowly building up our toolbox. We're becoming so smart at integrals. I'm very proud of you. Keep up the good work, and as always, take care.